The first questions that I've highlighted here are basically definitions. Gases generally have what? Well, we look at our choices. Low density, high density, closely packed particles, no increase in volume when temperature is increased, no decrease in volume when pressure is increased. We can throw out some of these as obvious falsehoods based upon what we know about gases. They do increase in volume when temperature is increased. That's Charles' law. So that one is false. They do decrease in volume when pressure is increased. That's Boyle's law, right? So that statement is false. Closely packed particles? No. That's only good for solids and liquids. So low density versus high density. So how do we break the tie there? All right, we go to the definition of density and we say, okay, for a given mass, is a volume of a gas relatively high for a given mass or low? If it were low, then that would make density high, and that would be B. If the volume is very large for a given mass of gas, then the density would be low, and that would be A, which is the answer. They have low density. All right, number 2. I usually start off asking you if you have any particular problems, and we should do that. Is there any one of these questions that just didn't click? No. If you think of one while we're going through it, just stop me and we'll deal with it. Okay, number 2. Pressure is. We've got several definitions in there. If we go through them one at a time, defined as the mass that an object exerts when at rest. No, let's go back to the definition. Definition of pressure is force per unit area. Now, we do have a whole host of different units of measure for pressure, but that's the basic definition. If we have mass, just mass, that doesn't cover anything. In fact, mass isn't a force. The second one says newtons, but it's not per unit area. So A and B can't be right. C says defined as the number of moles of substance divided by the mass. What would that be? Well, it's actually the inverse of molar mass, right? Grams or mass divided by moles is molar mass. It's nowhere near pressure. Defined as the force per unit area. There you go. That's D. Let's see, we're going to 3? Yeah, we're going to 3. Okay, SI unit of pressure is, okay, the pressure the value that's assigned for pressure is based upon this relationship. And the standard of unit for force is the Newton. So area would be derived from the standard unit of length, which is meters, be meters squared. 1 Newton per meter squared is given a special unit, the Pascal. Right? That's why E is the answer. Number 5. Let's see. I found out how to make these guys work. You have to press really hard. A glass column is filled with mercury and inverted in a pool of mercury. What does that sound like? A barometer. You can't fill a glass column if both ends are open, so one end has to be closed. Right. The mercury column stabilizes at a height of 725 millimeters above the pool of mercury. What's the pressure in atmospheres? This is one of those, remember what I said about word problems? The first rule for a word problem is to confuse. And one of the ways they try to confuse you is giving you a lot of information you don't need. The question is, what's the pressure in atmospheres? Well, the pressure is 729 millimeters of mercury. That's all you have to focus on. And then you unit convert to atmospheres. You just need some way to go from millimeters of mercury, right, in the denominator, so it'll cancel and leave us with atmospheres. So you just need to know what is the relationship there. Remember? 760. Okay. So divide 760 into 729, it's going to be less than 1, right? But not much less than 1. Right. So E is too far from the fraction. B is still too far from the fraction. A is the wrong direction. Right? And 456 atmospheres is just ridiculous. So the only logical one is C. And if you do the calculations, you'll find out that it is 0.959. All right. Okay. Next one I have highlighted is 6. Local weather forecaster reports the current barometric pressure is 30.4 inches of mercury. What's that in atmospheres? You need another conversion factor, right? 30.4, period. 34.4 was it inches of mercury? Right? Look in useful information. I give you all these conversion factors. So this is inches, and this would be atmospheres. All right, so for 1 atmosphere, how many inches of mercury we're talking about? 2992. Right? So we divide 2992 into 30, and we ought to get something just a little over 1. Excuse me. I'm sorry, millimeters of mercury. No, I'm looking at the wrong one. Close my eyes and start again. 6. Okay. So we ought to be in the neighborhood of 1, but not exactly 1. We'd have to be exactly 30.4 to be 1. So that's why it's not C. But A is closer to the fact. There you go. I didn't highlight 7, but I was looking at it. How about 8? And so far, what we've demonstrated is dimensional analysis, solving chemistry problems. I think I mentioned that at the very beginning. A lot of problems in chemistry are solved simply by converting units. Let's see. Oh, wait a minute. 8. I'm getting ahead of myself. 8. The air pressure in the inner tube of a tire on a typical racing bike is 112 psi. Convert this pressure to atmospheres. 112 psi. We want to convert that to atmospheres, was it? Yeah, atmosphere. You ever owned a 10-speed bicycle? I used to ride one from my house through Atlanta traffic to school downtown Atlanta. That was a challenge. Not only did you have to dodge the cars, but you had to watch out for the storm grates because they were oriented this way. So your tire would go right into them, and you go over the handlebars. So I'd have a rearview mirror and I have to look and it's swerve around them real quick. I was in better shape then. So I would keep up maybe 20-mile-an-hour speed. Aaron Cooper. Okay. There's Aaron. All right. Anyway, my bicycle wasn't one of these racing bikes. It had small tires, but I think it was 85 psi. The smaller the tire, the higher the pressure for some reason. I haven't looked at it mathematically to see if that makes any sense. But they're set at 112 psi for these racing tires. They're about as big as my finger. And we want to convert that to atmospheres. Yes. Okay, so what's the relationship here? If we want atmospheres in the numerator and cancel psi, Remember that one? 14.69. Right. So estimating that one's a little beyond me right now. 14.69. And that's 7.6, three significant figures. 7.62 atmospheres. So B is the answer. Now we got a, how do we express Boyle's law, Avogadro's law, or 9? Boyle's law, remember that's the relationship of pressure times volume is a constant. So let's see. The answers are probably going to be changed a little bit from what you would normally consider Boyle's law, just so that we see if you understand it. The first one says equal amounts of gases occupy the same volume at constant temperature and pressure. Which one is that? That's the next one. That's Avogadro's, right? Okay, so we got 10 down there already. Avogadro says that volume relationship with moles is a constant. So this one is A. We'll just get that one out of the way because it's the same set of answers. B for number 9 says the volume of a fixed amount of gas is inversely proportional to its pressure at constant temperature. Yeah, that's a good. That looks right on the money to me. The rest, if you go through and look at the rest of them, they should be false. Charles' law. Let's not forget Charles. So Charles' law is the relationship of volume to temperature is a constant. And what relationship are we talking about here? This is a direct proportion. As this one goes up, that one goes up in order to keep that one constant. Same for this one. This one's in the inverse relationship. So as this one goes up, that one has to go down to keep that one constant. Okay, so Charles' law, we've already looked at A and B, and C then would be the volume of a fixed amount of gas is directly proportional to its temperature in Kelvin units. Yep, that's it. Now, this has to be Kelvin. Remember why? I know we just talked about it 2 days ago. Why does the temperature have to be in Kelvin? You remember? Yeah, the negative numbers, right? If you go below 0 in Celsius, you end up with, you've changed the value, right? You go from a positive to negative like that, and now it's not constant. So we got to keep the temperature in the positive range. And that's where Kelvin comes in, because 0 in Kelvin can't go any lower. It's absolute. All right. Moving on. That was Rascal Flatts, wasn't it? Moving on. Didn't they do a song? Yeah, they did a song called Moving On. I don't even think they're together anymore, are they? I haven't seen any new stuff out of them. Let's see, where were they based? Arkansas or Missouri? One of those places. Anyway, 15. Gaseous chlorine is held in 2 separate containers at identical temperature and pressure. The volume of container 1 is 1.3 liters, and it contains 670 moles of gas. The volume of container 2 is 2.33 liters. How many moles of gas is in container 2? All right. What type of problem is this? Remember the 2 types, before and after or state. We see 2 volumes there. We only see 1 moles, right? 1 amount. So that's a before and after, right? So if we're before and after with volume and moles, 1, 1, and 2, 2. Whose law is that? Avogadro, right? So the first condition is 1.13 liters, 1.30 liters. And how many moles? 6.7 moles of gas. 70 moles. And the second one is 2.33 liters. So I guess this one's going to be the unknown. Yeah, it's asked for how many moles are in container 2. So remember the equivalence we have for this one. V1 over N1 equals V2 over N2. And this is our unknown. So I'm going to put it on this side over here. Bring it across, goes to the numerator. This one stays put. That one comes over here. And this one goes over there. So there's your rearranged formula. Okay. It's just algebra. So now we can plug in the values. V2, 2.33. I'm going to leave the units out simply because it's takes up too much room and time to write them. See, N1 is 6.70, and then 1.30. Okay, so the number of moles would be 2.33 and 6.7 times that, and 1.3 divided into it. 1.20 moles. And why do I not? Oh, wait a minute, I read it wrong. I got my calculator set up to spit the numbers out in scientific notation. And I didn't look at the exponent. I just looked at the coefficient. So I had to move my decimal. Should be 12 moles. Yeah, A. All right. See how easy it is to make mistakes. All right. And by the way, it didn't matter if it was chlorine gas. Could have been anything, right? A gas is a gas is a gas. As far as these laws are concerned, it doesn't matter. Now, if you're going to go in there and smell it, it might make a difference. 18. Body temperature is about 309 K. All right, 309 K. Is that right? 309 minus 273, right? Well, they're off by a degree. 309 K. Let me do that again. It is 273, isn't it? Yeah, they're off by a degree. Body temperature is 37 Celsius. That's only 36 Celsius. Maybe that's why they say about. It's about 309. That's somebody who's headed for hypothermia. On a cold day, what volume of air at 276 must a person with a lung capacity of 2.2 liters breathe in to fill the lungs? All right, so when they breathe in the air at 276 K outside their body, goes into their lungs and it heats up because it extracts heat from your body. And then that volume is based not on 276, but on 309. So what we've got here is this is T1, and we're talking volumes, right? T2, actually, that's not T1. That's T2. T1 is outside the body at 276. Okay. We want to know what this volume is inside the body. So, wait a minute. With the lung capacity, no. Inside the body, we know the lung capacity is this. Am I confusing anybody? This is the temperature inside the body the lung capacity here. This is the temperature outside the body. We want to know how much of this air at that temperature do we have to suck in to fill our lungs. That's where we're headed. So this is the unknown. So this is Charles' law, right? V1 over T1 equals V2 over T2. And we're looking for V1. Okay. So now we can plug in the numbers. I finally got it figured out which one was which. And that's why I do this, so that I can extract the right numbers to the right place before I put them in my formula. So V2 is 2.2 liters. T1 is 276. And T2 is 309. So V1 is how much air at 276 do we have to draw in? 2.2, 276, and 309. 1.97. Rounded off. That's how much of the cold air we have to draw in. Number 20. Okay, you're holding two balloons, an orange and a blue balloon. Okay, I don't know what the difference in volume is yet. So we'll just do that, and then we'll adjust the volume once we find out. Orange and a blue balloon. The orange balloon is filled with neon, and the blue balloon is filled with argon. The orange balloon is twice the volume of the blue. So this one is twice the volume of the blue. Let's redraw it. Give it twice the volume. Okay, the orange balloon has neon in it. This one has argon. Okay, and this in the volume here, volume of neon equals 2 times the volume of argon. That's how we say that in math terms. Which of the following best represents the mass ratio of neon to argon? So we want mass of neon ratio to mass of argon. Okay, what do we also know? Well, we have to assume, we're given the volume, we have to assume that the pressures are the same. You know, these balloons, they're held at the same atmospheric pressure. So those are equal. Temperatures also, we have to assume that the temperatures are equal. I should have put orange and blue, but I think it's easier to follow if I do this. Okay, so if the volume of the neon is twice the volume of the argon, what's the ratio of the moles? The moles of neon equals twice the moles of the argon. So we have twice as many neon atoms in there as argon. So what's the secret number for mass relationships? Molar mass. Right? What's the molar mass of neon? We're just estimating here. So neon is roughly 20. Like 20 atomic mass units per neon. Argon should be around 40. Yeah, around 40. Atomic mass units per argon. Right? Per atom. Per atom. So if we have twice as many neons as we do argons, then if we say, let's just say argon, our value is 1. And neon, the value would then be 2, right? 1 times 2 is 2. So twice as many neons means our mass is 40 and our mass here is 40. They have equal mass ratios, 1 to 1. Okay? Are we still puzzling? The difference in mass is due to the difference in weights of the atoms. That's what we're saying. So if we can say that this has twice the volume, it has twice as many atoms in it. If it has twice as many atoms in it, then than argon, if they were the same mass, it would have twice the mass. But it actually has half the mass. So half of that would be equal. We have equal masses of neon and argon. Let's see, what's another way? If we said 20 grams per mole, how about that? And then 40 grams per mole. Okay. If let's just pick an arbitrary. Let's say we have 1 mole here. How many moles do we have over here? 2. Okay. So 2 moles of this gas would be 40 grams, and 1 mole of that gas would be 40 grams. Does that make more sense? Okay. Let me see here. Let's skip a few repetitions. Go down to 29. Let's see. A gas sample is heated from -20 to 57, and the volume is increased from 2 liters to 4.5 liters. If the initial pressure is 0.14, what's the final pressure? Whoa. We got lots of before and after here. Okay, so we have a trapped gas, which means the moles aren't going to change. So if we have our P1 V1 over N1 T1 equals P2 V2, the combined gas law, that's where we're headed. Oops. T2. These are the same, right? So they go out. And we're left with P1 V1 over T1. So what we have to do is decide what's what. P2, V2, and T2. Okay. Beginning pressure. We're going from -20 to 57 temperature. I said pressure, but temperature is, take them in order. -20 degrees C versus 57. Let's see, that's 0.0. And it goes to 57 degrees C. Okay. Simultaneously, the volume increases. As the temperature increases, the volume increases. That makes sense. Increases from 2 liters to 4.5 liters. So it goes from 2 liters, numbers in the right place. 2 liters to 4.5. Yeah, 4.5 liters. There we go. Now our pressure goes from initial pressure 0.14 atmospheres. 0.140 atmospheres. And this is the question. That one right there. So we just need to rearrange this, or you can plug the numbers in as is and solve it either way. P2, we're going to solve for this one. So I'll leave that one there, but I flip it so it's on this side. And then equals P1 V1 T2 over V2 T1. T1's already over here. Let's see. Wait a minute. That's not right. Yeah, it is. Yeah, because this one stays put. That one comes over here. There they are. That stays put. This one comes over here. There they are. Now we can put in the values. P1 is 0.14 atmosphere. V1 is 2 liters. And P2, what did we forget to do? We got a negative here. We better convert to Kelvin. 273. plus 273. So 273 there is 253. That would be T1. That's down here. 273. And T2 goes up on top. So what's that? 330. Right? Carry your 1. 12, carry 13, carry your 1, 3. 330 Kelvin. And then V2 is 4.5. There we go. Let's see if that turns out to be what the key says it is. 2 times 330 times 4.5 divided and 273 divided. I get let's see. It's in standard notation. Did I do that right? P1, yeah. V1, yep. 330 is T2. I calculated that right. Yeah. Yeah, 330. And then the bottom is B2. Yeah. And 273. Okay. 0.14, 2 times 330 times 4.5 divide and 273 divide. Okay. I'll move the decimal place 2 to the left because I've got it in scientific notation. 0.752 atmospheres. Now, why does it say 0811? Made a mistake somewhere. Let's see where it is. Let's see. We're going from minus 20 here, which would be 253. Oh, that was dumb. Let's see. I had 273 on there, 273 times, and then 253 divide. Now we're in the ballpark. 812. Close enough. E. It's a good thing I'm not chewing gum or I wouldn't be able to walk. Okay. 30. A sample of oxygen has a volume of 1.72 liters at 27 degrees and 800 torr. How many oxygen molecules does it contain? All right. Before and after or state. This is a state, which means we need the ideal gas equation. PV equals nRT. And the question is asking for how many oxygen molecules. All right, so we're headed for a counting number, which in this case is N. All right, so N equals PV over RT. That only gets us part of the way to the answer. It tells us how many moles, doesn't tell us how many molecules yet. But we can plug in the values for pressure. All right, pressure is 800 torr. Well, 800 torr needs to be converted to atmospheres. Right? And volume, is it in liters? Yeah, 1.72 liters. Okay, this is atmospheres. R, remember what R is? 206 liter atmospheres per mole. Okay. And then temperature has to be in K. So 27 plus 273. There we go. Now that's going to give us moles. And rather than tack on a conversion factor for the other, I'm going to do this one first. So 800 divided by 760 is 1.053. 1.053 here times 1.72 divided by 0.08206 and divided by 300. So this is 7.35 times 10 to the minus 2 moles. We want to know molecules. So what's the magic number? Avogadro's. I don't think I have Avogadro's in the useful information, so you have to memorize this one. 6.022 times 10 to the 23rd. 6.022 exponent 23 times. So I get 4.43 times 10 to the 22nd molecules of what? Oxygen? Yeah, oxygen. That's A. Okay. All right, who's next? We'll skip a few. Come down to 37. All right, which conditions of pressure, temperature, and moles respectively are most ideal? Well, I think I mentioned high temperature, and low pressure. Low pressure implies low moles. So let's see, it's in pressure, temperature, moles order. So it'd be P, T, N order. So pressure would be low. That's either B, D, or E. And the next one is temperature. B says low temperature. Nope, can't be. D says high temperature for both of them. And then the last one says low moles, so E has to be it. Okay. Process of elimination. Also known as test-taking technique. All right, number 40. I think. Yeah. 41 gram sample of neon gas exerts a certain pressure in a container of fixed volume. What mass of argon is required to exert half the pressure at the same condition of volume and temperature? All right, if we have 41.1 grams of neon gas, that's where we start, of neon. The way we relate the gases is not by mass, but by moles. So we need to convert this into moles of neon before we can say anything about it in terms of conversion to the other. All right, so neon is 20.18 grams per mole. Right, let's find out what that is. It's going to be in the neighborhood of 2.04 moles of neon. Okay. Now that we know how many moles, sorry, yeah, of neon we're talking about, if it's at fixed volume and the pressure doesn't change, and we have to also assume that temperature, volume, yeah, same temperature and conditions of the same volume. Okay, that's given in the problem. We want to know what's the mass of argon. Well, argon would have the same number of moles, wouldn't it? Yeah. If all of those are the same, pressure, temperature, same, the only difference between the two, well, actually, if those are all the same, then the sum number of moles is the same. Yeah, moles is the same. So we can say this. That's actually moles of argon. Now we can convert backwards. Grams per mole. And argon would be 39.95. I'm using better than estimates here. 39.95 times is 81.4 grams of argon. Oops. What did I do wrong? Okay, let me read that again. So many gram sample, certain pressure in a container of fixed volume. What mass of argon is required to exert? Oh, half the pressure. If it exerts half the pressure, it has half the number of moles, doesn't it? Yeah, that's where I messed up. So this should be 1.02 moles of argon. Half the pressure means half the moles. All right, so it'd be half of this. Right? Let's see. There's be 4 and then 40.7 grams. There we go. See, whoever made this problem up, they said, okay, what kind of mistakes could be made here? Missed that part about half the pressure. So we just say they're equal, come out with that answer, select that answer, and get it wrong. Sneaky people. All right, we'll skip a few and get down here to 49. For which gas are the molecules diatomic? Okay. We memorize diatomic elements, right? We know helium is monatomic because it's a noble gas. Chlorine is one of the diatomics, right? Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are all diatomic elements, right? Under standard temperature and pressure conditions, right? So chlorine's a good answer. CH4 is not diatomic. Actually, what would it be called? It would be pentatomic, right? It has 5 atoms. And ammonia would be a tetratomic. Okay. So chlorine is the only diatomic molecule in this group. All right. Next, 52. Let's see, the mass of 1.12 liters of gas Y at STP is found to be 6.23 grams. The density of gas Y is. All right. So let's put what we know up here. This is gas Y. Gas Y has a mass of 6.23 grams is the mass. 6.23 grams at 1.12 liters. And volume equals 2 liters. So what's the density of the gas? Okay. There's 2 approaches to this. We can take the formulas that we need to answer the question and combine them into one and then plug the values in and get the answer. Or we can do it step at a time. Let's do it step at a time. So if we're asked to calculate the density, we need to fill in values for this one, mass per unit volume. Right? We got the mass right there. What we need is the volume. Oh, wait a minute. Density of the gas, mass of 1.126. Wait a minute. That's easier than I thought it would be. Let's just divide grams by liters, isn't it? I was making this problem a lot harder than it needed to be. All right. So we got 6.23 grams. I guess this is just to see if you know what density means. See if your instructor remembers what density is. So I get 5.56. 56 grams per liter. Yeah. I was overthinking that one. All right. 53. 53. Oh, okay. So we're going beyond with 53. Same gas with a mass of 6.23 grams. 6.23 grams. And 1.12 liters volume. Liters at standard temperature and pressure, correct? Yeah. What's STP for a gas? Standard temperature is 0 degrees C or 273 K. Standard pressure is 1 atmosphere. 1 atmosphere. Okay. So if we're going to calculate the molar mass of Y, that I abbreviate molecular weight, is the mass of the gas per unit moles. How many moles do we have? Okay, so this one we do have to use a state function, which is the ideal gas equation. Like PV equals nRT. We need to find out how many moles. We already have the mass. We need the moles. So N equals PV over RT. So pressure is 1 atmosphere. Okay. Volume is 1.12 liter. R 0.08206 liter atmosphere per mole K, and temperature is 273. Okay. That'll give us the number of moles. And I get 9994.7 times 10 to the minus 2. Say again, the mass is 6.23 grams per. Why am I keeping so many digits? Avoid rounding error. 6.23 and divide that into it. I get 125 to 3 significant figures, grams per mole. Yep. Okay. The other way you can solve this problem is to say, all right, if we need moles, we already have mass, then the molecular weight would be mass on top, and then what's equal to moles here? PV over RT. And then we flip it, because denominator of the denominator is the numerator. So we have nRT over PV. Substitute your values and you got the number. There's 2 ways to do it. All right. Let's see. We're down to 55. Argon has a density of 1.78 grams per liter at standard temperature and pressure. How many of the following gases have a density at STP greater than that of argon? Okay. Well, let's see. Density of argon is given as 1.78 grams per liter. 1.78 grams per liter. And the others we're looking at are chlorine, helium, ammonia, and nitrogen dioxide. All right. If we're at standard temperature and pressure, they're going to have the same volumes also, right? But they might have different, let's see. No, they have the same number of moles also. Right? So really the comparison is between the molar masses of the atoms, because that's where the difference in density, that's where the difference in that term right there, that's where it comes from. Right? So if you have equal moles of everything, all we have to do is compare the values of molar mass. Argon is 3995. Chlorine is, let's see, 3545 times 2. 0, 9, 10, 70, 90. 2.02, right? Ammonia, 14.01 and 3.03, 1704. And NO2 would be 14.01 plus 2 times 16 is 32. 4601. Now the density, under the same conditions, the density is going to be determined by the difference in mass, because we have equal moles of each one. So which ones have a density greater than argon? Right? This one and this one. Chlorine and nitrogen dioxide. So, it says how many of them? Yeah, 2 of them. Okay. So the key to this one is recognizing that you have the same number of moles of each one, occupying the same volume. So the only comparison you need to make is their molar masses. All right, what's next? Ooh, 56. How am I going to explain this one? All right. Which of the following is the best qualitative graph of pressure versus molar mass of a 1 gram sample of different gases at constant volume and temperature? Okay. Pressure, I assume, is going to be on the y-axis. Okay. And molar mass is going to be down here. So as we get heavier and heavier, which way is this graph going to go? This way, that way, is going to have a curve in it. So what we need to do is say, what can we say about the comparison here? If it's a 1 gram sample of each one, then the difference between the gases has to do with, at standard temperature and pressure, well, pressure is going to vary. So standard temperature, volume, and obviously moles. So the difference here is going to be between pressure and molecular weight. So if we increase the molar mass of a gas, what does that do to the, if it has the same number of moles, and we change the molar mass, the molecular weight, say the molecular weight's going up as we go through our various gases. What's happening to let me see. If it's a 1 gram sample, okay. If it's a 1 gram sample, then as the molecular weight goes up, for a 1 gram sample, of gases. As the molecular weight goes up, grams per mole, what happens to the number of moles? Right? Look at this as a relationship. Right? As grams goes up, moles has to go down, doesn't it? Okay. So as grams go up, moles go down. Let's say its molecular weight goes up, moles would go down. We decrease the moles. So as molecular weight gets bigger, the number of moles decreases, which decreases the pressure, doesn't it? Okay. So it's going to have a slope this direction, but what type of relationship is it? We can say that pressure, molecular weight is a constant. Pressure volume in RT, that's operative. What are the others? Which ones did we use? Molecular weight. We just used two of them. Molecular weight equals mass per moles. Okay, so if we're looking for relationship, how does P change with MV, molecular weight? We want to get this one over here. And the common term is moles. So moles over here, mass over molecular weight. Okay, so then I can say PV equals mass per molecular weight, or T. Okay, and we want to get the terms for molecular weight and pressure on the same side. So we'll bring this one over here. Pressure times molecular weight equals mass RT over volume. Okay. The mass is constant. We said it 1 gram. So that's constant. R is a constant. Does temperature change? No. Temperature doesn't change. How about volume? Those are different gases at a constant volume. That doesn't change either. So all of these are constant. There we go. This relationship is constant, which means as pressure goes up, molecular weight goes down, and vice versa. So where did we see that before? Boyle's law. PV equals constant. So this graph ought to look like Boyle's law. As molecular weight goes up, pressure goes down. It ought to look like that, a hyperbola. And none of these fit that. Okay, that makes a whole lot more sense to me now. We couldn't get away from using math. I try to be intuitive when I can, but sometimes it just doesn't work. All right. 58. Let's see what we got here. Given the reaction, 2 ammonias plus 3 chlorines yields nitrogen and hydrogen chloride. Okay, so let's put that one up here, just so we've got it as a reference. They're all gases. Okay, so I'm going to leave the gas phase indicator out of it, just to conserve space. And HCl. Now this is going to be hydrogen chloride because it's a gas. If it were dissolved in water, it would be called hydrochloric acid. Okay. All right, now what's the question? You react 5 liters of ammonia and 5 liters of chlorine. 5 liters of ammonia, 5 liters of chlorine. Okay. Measured at the same conditions in a closed container. Calculate the ratio of pressures in the container. The ratios of pressure in the container. All right. Pressure on this side versus the pressure on this side. Pressure of, wait a minute. No. Final minus initial. Yeah. So this would be initial. This will be final. Actually, no, that's not right. Because we're given absolute amounts. One of these is going to be limiting and the other is excess. So we've got to find that out first. Which one runs out? Okay. If we've got the same volume of each one, then we should have the same number of molecules of each one, right? At least when we start. The same number of molecules means for every 2 of these, we need 3 of those. So this one's going to run out because they have equal amounts. This one needs to be more. We're going to use more of those. So this one runs out, right? That one runs out, and we're left with this one minus what we had there. Right, so if we use up all of these, let's say 5 liters of chlorine, we want to convert that. How much ammonia does that mean? And since number of moles and the volume are directly related, right, under standard conditions, then we can say chlorine and ammonia like this, and use 3 here and 2 there. So 3 into 10 is 3.33 liters of ammonia were actually used. So what do we have left over? Well, we have 5 minus 3.33. Okay. So that's, excuse me, that's 7. And this is 3 from 9 is 6. This is 1. 1.67 liters of ammonia left over at the end. How many do we get over here? Well, if we start with 5 liters of this, we're going to end up with 2.5 liters here, right? Half as much. And we're going to end up with half as much over here. Okay? So what do we have at the end? We have this left over. We don't have any of that. We have this left over plus 5 liters. 2.5 plus 2.5. 7, 6, 6. So this is final volume. Final volume. What was the initial volume? It was 10, wasn't it? Yeah, it was 10. Initial volume is 10. And if we're going to ratio pressures, pressure is proportional to volume. So as the pressure goes up, volume goes up. Or as volume goes up, the pressure goes up. So if we're trying to find the ratio of pressures, all we need is the ratio of volumes. Okay, so we're looking for final over initial. Final over initial is equal to volume final over volume initial. Wait a minute. Pressure and volume are inversely related, right? Right, as pressure goes up, volume goes down. So it's actually inverse. So as this final pressure, if the volume, initial volume is this value, it's related to the final. Well, the ratio is inversely proportional. If we bring this one over here, PF times VF equals PI times VI. And that's like our P1 V1 equals P2 V2. Okay. So this is an important point. Since they're directly proportional, in this ratio, they have to be inverted. So back to this. The final volume is this. 6.67 liters. What was the initial volume? It was 10, wasn't it? Yeah, 10. We didn't have any product. So 10 is this one. And the ratio, PF over PI, then would be 6.67 into 10. Which is, I think, 1 1/3. If you calculate it out, 1.33 is the answer. Now, if we got them inverted, if we put 6.67 over 10, what would that give us? I'm looking to see if they anticipated that mistake. 0.67. No, they didn't. That 0.75 should have been 0.67, just to catch anybody. But this is key. I mean, you have to know what you're doing here, of course, but this is the key to the answer. The inverse proportion of pressure and volume, right? So that's why we have 2, 1, and 1, 2. Make these pop-ups. Number 61. Good. They're coming down to the wire. When 0.72 grams of liquid is vaporized at 110 degrees and 0.967 atmospheres, the gas occupies a volume of 0.559 liters. The empirical formula of the gas is CH2. What's the molecular formula? Okay. That looks like a hair pulling experiment. So I think it's important to draw out the information that we're given, then make sense of the problem. 0.72 grams of liquid. 0.72 grams of the liquid gas vaporized at 110 degrees C. Temperature equals 110 degrees C. I know we're going to have to convert it, so we might as well do it now. 383. Okay. And 967 atmosphere pressure. 0.967 atmosphere. Okay. Occupies a volume of 0.559 liters. 0.5 liters. There we go. All right. What's the molecular formula? What we can determine, if we're given CH2 as the empirical formula, CH2, we can determine the empirical weight of that. It's just 12.01 plus 2.02 equals 14.03 grams per mole. So we're looking for that multiplier. Okay. If we find out what the true molecular weight is from this data, then we're home free. So if we're looking for the molecular weight, right, the molecular weight would then be mass per unit moles. We got the mass right here, 0.72. What we need is the moles. So I think what we're going to need is the gas equation. Moles equals PV over RT. Pressure is in atmospheres? Yes. 0.967. Volume is in liters? Yes, 0.559 liters. And then R is our customary value. And temperature we calculated as 383 K. So we can calculate the number of moles and plug it in that formula. Is that right? Let me do that again. I thought so. I hit the wrong key. I'm still not convinced. Let me try it again. If I got the same one twice in a row. There we go. Okay, so I get this many moles. 7, 1, 0.99 moles. Divided into 0.72. I get 41.8 grams per mole. So if we divide 41.8 by 14.03, we should get our multiplier, or we round it to the nearest whole number. I get 2.984, which is about 3. So if that's 3 equals 3, then we have C3H6. Okay. All righty. Okay. Am I going to make it? I don't know. Skip a few, go down. Ah, there it is. Okay, 80. A little algebra going right here. So if M is the molar mass, M is what I call MW, molecular weight. R is the gas constant, okay? T is the temperature, pressure. Which of the following expressions represent the density of a gas? So if we go to density equals mass per unit volume, and we need something that's equal to mass. So let's say molecular weight, I'm going to use their abbreviation M, equals mass per unit moles. And then we need volume. So PV equals nRT has volume in it. Okay. So these have moles in common. So I'm going to solve for moles on this side. PV over RT. And then I'm going to substitute in for that. Right? PV over RT goes in here for that one. So molar mass is mass divided by PV over RT. Okay. Now, what we have in common here is both volume and mass. So I'm going to solve for mass. So I can put it right here. So leave mass over here. And let's do this. MRT over PV. Right? I just flipped this one the way it should be. Now I can go molar mass times pressure times volume divided by RT equals M. Okay. So far? Okay. Now I can substitute for M this expression right here. So D equals whatever that M is, big M for molar mass, PV over RT divided by V. Okay. V is in the denominator. That V is in the numerator. They cancel. And we're left with molar mass P over RT. But we wanted an expression for what? Density, right? Yeah, the density of the gas. So molar mass times pressure over RT is A, right? Sorry, I couldn't get away from math on this one either. If you can work this problem, you probably impress your math instructor. Okay, 81. I'm going to run out of time. One way to isolate metals from their ores is to react with a metal oxide with carbon, as shown in the following reaction. Okay, so 2 metal oxide solids, metal. Now this is metal. It's not molecular weight anymore. That represents the metal. Plus carbon, that a solid? Yeah. Yields 2 metals, solid, plus CO2 gas. Okay. This is the controlling reaction for the metal, the unknown metal that we're supposed to identify, I'm pretty sure. 34.08 grams of metal oxide, 34.08 grams of that metal oxide react with excess carbon. That's good. Excess carbon. And 4.37 liters of CO2 is formed. 4.37 liters of CO2 is formed at 100 degrees. 100 degrees C, I know we're going to need this. 373 K. And 1.5 atmospheres. So this is pressure, this is temperature, this is volume. What's the identity of the metal? Well, we know the mass of the metal oxide, right? Let's find out how many moles that is first. Because in order to identify the element, we're going to have to know its molar mass. We can't know the number of protons. We don't have the data for it. But if we can find out the molar mass of that metal, actually, let's find out how many moles we got first. PV equals nRT. Number of moles equals PV over RT. So the pressure is 1.50 atmospheres. The volume is 4.37 liters. 0.08206 for the bar. And temperature is 373. Okay, so we can find out how many moles we're talking about for that gas. Then we can relate it. Right? You can't go anywhere without moles. Three. And I get 0.2142 moles of CO2. There are a couple of approaches for this. We need to find out the mass of that. Yeah, we can find out the moles from this. We can do that first. 0.2142 moles of CO2. Convert that to moles of M. Or do we want to go all the way over here? We know the mass of this compound. It's 34.08 grams. If we knew how much oxygen was in that compound. Well, they're saying the formula is one of these and one of those. Okay. If this is the actual molecular formula of that compound, then this is, for 1 mole, we got 16.00. Now, I can't say that. We need to find out how many moles that is. So this is where we're headed. MO. So for every one of these, we got 2 of those. So we actually have 0.4184 moles of MO. So what's the mass of 0.4? If it's 1 to 1, 0.4184 moles of the molecule means 0.4184 moles of oxygen, doesn't it? Okay. So we can find out the mass of that oxygen, grams. There's one of them, 16. So 16 times 4184 is 6.853. 6.853 grams of oxygen. So we know the mass of that. We know how many moles there are, right? This is the moles of the molecule. It's also the moles of the metal. Then the molecular weight of MO equals mass, 34.08 grams per 4184. I'm sure I'm on the right track. Well, they got 4283. Maybe that's where I went wrong. This should be 2, shouldn't it? Yeah. If we double this one, 4284. There we go. That's probably where my mistake is. Am I losing? Are we okay? If we know the molar mass of this, then we can find out the molar mass of the metal. And I'll show you how that works. So this is 79.55 grams per mole. Okay. You know how we calculate the molar mass of a formula, right? You just take the molar masses of each of the elements times how many there are, right? We've only got one of each. So the contribution of this M plus the contribution of 16 is that total. So we just subtract 16. 6355 is the molar mass of M. That's why it's copper. Okay. And I think my mistake was right over here when I'd made that conversion to this one. Right. I probably would have gotten the right answer if I'd have used the right number. But this works also. As long as there are no questions. Okay. There's nearly always more than one way to work a problem. I knew the chemistry professor, I knew him pretty well at Concord until he retired, John Elkins. And he had a student who would work all this stuff out in his head. So he never would show his work. He'd get the right answers. And sometimes if he did work them out on paper, John would look at it and say, "What?" So, more or less story is there's always more than one way to work a problem. Okay, 82. This one's about to give out, and I'm out of time. Standard temperature for gases, 0 degrees. See. Standard pressure, 1 atmosphere. Okay, 1, 2, 3. Oh, I got more than okay. If you have to go, I'll understand. But I do want to finish this. Let's see. Right, that's where we were. I don't have time to do it on another day, so I'm going to finish now. If you have to go, then I understand. I'll have it posted by midnight tonight. 86. 142 milliliter sample of gas is collected over water at 22 degrees C and 753 torr. What's the volume of the dry gas at STP? The vapor pressure of water is 22 degrees at 20 torr. This is Dalton's law of partial pressures. So it's going to help to draw a picture. If we have water here and we're collecting the gas in a device that will measure it, let's say graduated cylinder, right? So we have markings on here. And then we have a reaction vessel here. Let's see, let's go over there. Right. And the reaction takes place over here, and we got bubbles coming up here. So the volume, this is gas up here. Okay. That gas is composed of, let's see, does it say what the reaction is? It just says gas. So we have a combination of gas here plus water vapor. All right. And as far as the volumes go, the combined volume of this one and that one equals 142 milliliters. Okay. We got an initial pressure is 753 torr. We have, excuse me, an initial volume and an initial temperature. So the initial temperature is 22 degrees. Yeah, okay. So the initial volume is 142 milliliters. Final pressure is 1 atmosphere or 760 torr. As long as we use the same units of measure, we can do that. We're looking for this volume here, and we got this temperature. Final temperature is 273 K. Now, this is the sticking point right here, because at that temperature, 22, is it 20? No, 20 torr. This is 20 torr. Right. So the value of the gas is 122. It's not 142. It's 122. Now this was, and I might come up with a different answer than this one. Oh, I'm my own worst enemy. That's milliliters. This is the pressure that needs to be modified. Right, 753, but part of that is water vapor, minus 20. It's 733. There, that's the change right there. Because this is water vapor, this is the dry gas. Okay? All right, now we can do P1 V1 over T1 equals P2 V2 over T2. And we're solving for a V2. Okay? So V2 is going to be P1 V1 T2 over V2 is going to be P1 P2. Now we can solve it. P1 is 733. V1 is 142. T2 is 273. T1 is 295. And P2 is 1 atmosphere, 760. There we go. The thinking part's over with, thank God. Now we just have to crunch numbers. 142 273, 295, and 760. Oops, I did something wrong. Let's go back. 33, 273, 295 divide, and 760 divide. Now we got 127 millimeters. Oh, none of these. After all that work, it's none of these. Okay. Yeah. All right. Let's see. Do we need to tackle this one? Oxygen gas generated by this reaction is collected over water at 27. Vapor pressure, how many moles of... All right. This is a stoichiometry problem, but it requires Dalton's law of partial pressures. So when you calculate the moles of your gas, which is only oxygen out of that one, when you calculate the moles, you have to start off with an adjusted pressure. Right? The pressure is not total pressure is 760 minus 26 and convert it back to atmospheres. All right. I'm going to leave that one. If you need to look at that one, then it's in another video. I'm trying to save time here and get to one that really, this one right here, 94. That's one that I wanted to be sure and get to. Okay. Marker. Nope. Go in here and get a fresh one. These things don't last very long. Okay. Here we have okay, my program that silences is not working now because I'm past the time. So we've got this vessel here with 3-liter volume. Yep. And it's connected through a valve to the other vessel that's only 2 liters. Okay. All right. Valve between the 2-liter bulb in which the gas pressure is 1.80 atmospheres. Inside this one, pressure equals 1.80 atmospheres with that volume. And the 3-liter bulb in which the gas pressure is 3 atmospheres. This pressure is equal to 3 atmospheres. Right? So the pressure of the 3-liter bulb is that one, the pressure of the 2-liter bulb is this one. All right. What we want to know is what's the final pressure if we open that valve and the temperature remains constant. Okay. So this is a Dalton's law of partial pressures. And what we're going to do is do a thought problem. Einstein was famous for those. We're going to make a thought problem out of this. We're going to say, what if we calculate the pressure of this total volume if this one is a vacuum? Because the total pressure is simply the pressure of the 2-liter plus the pressure of the 3-liter. So if we take them as separate gases, they don't have to be, but they can be separate, different gases. If we say this is a vacuum and we say, all right, we're going to expand this one into that space, what's the pressure now from just this contributor? Then we do the same thing for this one with that one as a vacuum, and that's its contribution to the total. Then we add them together. That's where we're headed. Okay, so let's say this is a vacuum. So this P1 V1 equals P2 V2. And this is initial. So the initial pressure is 1.80 atmospheres. And the volume at that atmospheres is only 2 liters. Then this is our unknown pressure. And the second volume is what? Huh? No, second volume. 2 plus 3 is 5. 5 liters. Okay, now we can solve for P2. P2 is simply 1.8 times 2, which is 3.60 divided by 5. .6 divided by 5 is 0.72 atmospheres. Okay. Now we do the same thing on this side. And we say, what's the P1? The P1 is 3 atmospheres. Right? And the volume 1 is 3 liters. And the P2 is still our unknown. It's a different P2, but P2 times 5 liters. That's the final volume. So now P2 is equal to 9 divided by 5. 3 times 3 divided by 5, which is 1.8 atmospheres. Now the total is 1.8 plus 0.72 equals 2.52. Okay? That's the final pressure. Now, does it make sense? When you open that valve, is it going to be any higher than either this one or that one? No, it can't be. Right? This one's going to lose a little bit. This one's going to lose a little bit. And they're going to meet in the middle somewhere. So the value has to be between 2 and 3. There it is. Now, your options here are 2.28, 2.52, and 2.4. Right? So you have to work it out to find the answer. We know it's not going to be 1.8. We know it's not going to be 0.72. 1.8 is for one of them. 0.72 is for the other one. You have to add them together. All right. Let's see, 95. Do we need to go through 95? Let me check it out and see if we've done one like it before. If we have, we'll skip it. The partial pressures of methane, nitrogen, oxygen gas in a sample of gas were found to be 135, 508, and 571. Calculate the mole fraction of nitrogen. Okay, the mole fraction of any gas is proportional to its pressure. The pressure of the gas, in this case, nitrogen, right? Pressure of the gas, nitrogen, plus the total pressure. Right? So the pressure of nitrogen in this one was, let's see, the middle one, 508. Try that again. 508 millimeters of mercury. And then we have 508 on the bottom, of course, because it's part of the total. And then we add the other two, 135 plus 571 for the other two gases. And that mole fraction is a simple calculation. And I get 0.42, 0.42 mole fraction, C, 0.418. Well, if I carried it out, it'd be 418. 3 significant figures, yeah. 418. And mole fraction has no units of measure, right? We just have to know where it comes from because this is millimeters of mercury and this is millimeters of mercury. The units cancel and will leave us with just a pure fractional number. Dalton's law of partial pressures. Total pressure of a mixture of gases is the sum of the partial pressures of all the compounds. That's it. 96 is D. And, oh no, we got another one. 103. Let's see, calculate the root mean square for velocity for O2 molecules in a sample of O2 gases, 11.8 degrees C. All right, 103. All right, we're given oxygen gas at 11.8 degrees. 11.8 degrees C. And R is a different value here. It's 8.3145 joules per k-mole. All right, what's our formula? Right. I gave you that in useful information. Root mean squared is at the bottom of the page. Square root of 3RT over M. Root mean square velocity, I think we used that one. RMS velocity equals the square root of, I even forgot it already, 3RT over M. 3RT over, and that's molecular weight. Okay. So R is going to be 8.3145 joules per mole K. And then we got to multiply that, excuse me. Multiply that times 3. And then T is going to be plus 273. Let's go ahead and use 15 since we got that there. It's 5, 9, 4, 8, 284.95. 284.95 K. This is the tricky part. All of these units are in SI. So when we say molecular weight, we normally say grams per mole. But for this calculation, it needs to be kilograms rather than grams. So the molecular weight of oxygen is normally 32 grams per mole. And we need to convert that to kilograms. Cancel the grams, kilograms per mole. So this is 10 to the minus, 10 to the third, excuse me, 10 to the third grams in the denominator means 32 times 10 to the minus 3 kilograms per mole, or 3.2 times 10 to the minus 2. I just leave it this way because the calculator doesn't care if it's scientific or not, right? So we can put it in like that and the calculator will work. So let's see, 3 enter and 8.3145 times and 284.95 times divided by 32 exponent minus 3 divide. So I get 2.22 times 10 to the 5th, and we have to take the square root of it. So I hit the square root button, and this is in meters per second. 4.71 times 10 squared meters per second. Oh, move the decimal 2 places, 471 meters per square meters per second. So close enough. C. I don't know what the speed of sound is in meters per second. I mean, I'm kind of intuitive about miles per hour or feet per second. It's roughly 1,000 feet per second. Let's see. Any more? Of course. 109. Which of the following is included as a postulate in the kinetic molecular theory of an ideal gas? Okay. The distance between gas molecules is small compared with the size of the molecule? No, it's huge. The distance between these molecules is massive. B, all collisions between molecules are elastic. That's it. What do we mean by elastic? It means an elastic collision in physics is where two objects hit each other and their energies are conserved. The total energy, kinetic energy of the impact is conserved. So for their velocities may change, but the total kinetic energy is conserved. That's elastic. And that's basically billiard balls. What would be a totally inelastic collision? It's like taking an egg and dropping it on the floor. It just goes. All the energy it had from that fall is now gone. It's converted into heat. Let's see. So that's B. Yeah, B for 109. Any more? Graham's law. Okay, what's Graham's law? Graham's law in words essentially says that the rate of effusion of a gas is inversely proportional to the square root of its molar mass. Right? So the bigger it is, the slower it moves through a barrier with little holes in it. Oh, it's never ending. My fault. I picked too many. 116. Hydrogen and chlorine gases react to form HCl. You and a friend are on opposite sides of a long hallway. You've got the hydrogen, your friend has the chlorine. You both want to form hydrogen chloride in the middle of the room. Which would be the following true? What we're getting at here is who needs to release their gas first? Which one travels the slowest? The biggest one, right? The chlorine. So the person with the chlorine has to release first so that it has time to get to the middle of the room before the hydrogen does lickety-split from their side and ends up in the front. So which one is that? Your friend should release the chlorine first. That's it. B. (117) Order the following increasing rate of effusion. All right. The faster they go, the smaller the molecule. So the smaller one has the higher rate, is on the farthest side. The methane is the lightest molecule, then nitrogen oxide, nitric oxide, I think they call it. Then fluorine, then NO2, and then chlorine. Chlorine's the heaviest, so it's the slowest. And if we do increasing rate of effusion, it's just the opposite from their molar masses. 118, because real gas particles have attracted, let's see, because real gas particles have attraction for one another, real gases act most ideally at STP. That's sort of true. Not most ideally. They do act ideally at STP, so it's kind of questionable. How about B? We assume gas particles have negligible volume. Well, what does that have to do with the attraction for one another? I mean, that's true, but it's not related to the attraction of molecules. C says 1 mole of an ideal gas at STP has a volume of 22.4. Well, that's true, but again, what does it have to do with attraction of real gas particles? That's the real constraint on our answer. D says real gases act more ideally at higher temperatures and lower pressures. Yes. So D is similar to A, but it's better. Okay, choose the best answer. A. The following, which would be expected to have the lowest van der Waals correction for intermolecular attractions? This is 124. Okay, van der Waals attraction requires that we make attractions for corrections for attractions. What we want is a molecule with okay, we're looking for nonpolar if we can find it, and the lowest London dispersion forces. Okay, do we have nonpolars in there? Yeah, hydrogen, chlorine, and oxygen. They're all nonpolar. Ammonia is polar. So what's the difference between hydrogen, chlorine, and oxygen? It's the size, right? Size. What we learn is that the bigger the molecule or the bigger the atom for noble gases, the stronger the London dispersion forces, because the electrons have more space to move around and they can be unevenly distributed more frequently in a large molecule than they can in a small. So the lowest I keep saying van der Waals, they're related. London dispersion forces, the lowest is going to be the smallest molecule, which is hydrogen. Right? So we found the nonpolars, and now we found the smallest molecule for the lowest London dispersion, and that's hydrogen. Okay, 132. Maybe what I'm going to do is just skip all the definitions, because that's just rote memory. A manometer is attached to a sample of gas that occupies a volume of 2.34 liters. The mercury level in the arm of the manometer attached to the gas sample is 24.3 torr, lower than that of the arm open to the atmosphere. Atmospheric pressures, blah, blah, blah. What's the pressure of the sample of gas? Okay, this needs a picture. Definitely needs a picture. So our manometer, this is the reaction vessel, right? And it's connected by, say, a valve. It's connected to this manometer, which goes up like that. Okay, it's open to the atmosphere. So we've got 1 atmosphere pressure here. And our units are in torr. So this is 760 torr bearing down on this side. And then we're also told that the volume here is 2.34 liters. That may or may not be useful. The mercury level in the arm of the manometer attached to the gas sample on this side is 24.3 torr, lower than that on the arm of the other side. So this one over here is like that. This one over here is like this. And the difference between the two is 24.3 torr. Right? Yeah, lower than that. Atmospheric pressure is measured at 1.23 atmospheres. Okay, so that's wrong. It's 1.23 atmospheres. And our answer is in torr. So what is this in torr? It's 1.23 times 760. Do that again. Yeah. 935 torr, which is millimeters of mercury. Okay, so that's bearing down here, but what's the pressure of the sample in here? Well, it's 935 torr in excess of that difference, right? So the total is going to be this difference plus atmospheric, right? 969, correct? No, 959. 2, 4. Yeah, 959. E. I have to draw a picture. These are not the kind of problems that can work in my head. Okay, I hope we're close to the end. Okay. I kept you long enough. Way, way long enough. So we'll, let's see, next Tuesday, we'll have an exam on this material and we'll go in the lab and do waters of constitution and hydration. We get to play with fire. Okay. And heat up samples and make the water go shh. So don't forget to prepare your lab notebooks. I'll do a check on those. All right. And I guess, let's see. We had at the beginning 1, 2, 3, 4, 5, 6. We're only going to have 4 left because we lost 2. Right? We lost Matthias and we just lost Hafsa. So I guess if all 4 of you here, we can have 2 groups. But we're done for today. Now I'm going to go in and grade some submissions in Brightspace. I know some of you sent crossword puzzles. Right? If you haven't seen them yet, you know you've submitted them. I'm going to get to them this afternoon. And modify the final grade in Brightspace so it's current. All right, so we can end this deal right here.